Here we see water oscillating, but it's not because we're shaking it side to side, it's because of up and down. And another thing that we can sort of model it to is a parametric oscillator. But what is a parametric oscillator? So here we have a classic parametric oscillator. And this is a pendulum where you change the length of the string. And only at certain frequencies does it get excited. So why does it get excited? Well, if we look at the forces, we can sort of see how it gets excited. Now, just for reference, we pull the string up here, let it out at the apex of the swings, and then pull it back. Pull the string back up as it swings back through the equilibrium. So, what are the forces on this? Well, we know gravity is a constant, so there's a constant force of a gravity pulling down. Well, gravitational forces have been said to be restoring forces, and that holds true with this system. We see that if the pendulum is away from equilibrium, gravity is going to make it swing back to the equilibrium position. And essentially, this is how a normal pendulum oscillates, is gravity just keeps pulling it down and converting the potential energy to kinetic. Now, there's also the other force of the tension of the string. And that's what's changing in this case. Because when we pull the string in, we have an increased tension of the string as it's pulling it up and changing the position of the bob. So we have increased tension here, and pulling up here again, increasing the tension here. Now, we essentially remove all tension on the apexes as the string is being let out, because therefore the string is no longer holding the bob up and it's just letting it fall. But how does this excite it? Well, since we're not looking at instantaneous changes in a string length, we're looking more of a function and more of like a sine or a cosine curve. Well, essentially what that does is it allows the pendulum to start accelerating downwards towards the equilibrium and gaining a velocity. But at the same time, we have the tension of the string also pulling it towards the center of the pivot. And essentially what that does is the combined vector pulls it also towards the equilibrium, and essentially accelerating it more than it would normally just due to gravity. Now it does this each time it swings out from equilibrium. And since there's no tension pulling it back in on the other side, since we're letting it out as it swings out, this constantly adds velocity each swing, and it's exciting it each swing. And amplitude increases, all the good stuff. Now, there's only certain frequencies that do this, and certain phases. We have to always add the energy in at the equilibrium, and always let it out when it's far away from equilibrium. So as we can see here, the string goes up, and down, for the same of one period of the oscillator. So essentially, the driving frequency of the string is equal to twice of the natural frequency of the oscillator. Now, we need to make sure that this water is a parametric oscillator. So we're going to look at the drive frequency versus the water. The arrows here are to help us. The green one is the driver, and the blue one is the water. And as we can see, that the driver is sort of going at roughly twice the speed as the water, which is quite useful given the fact that that's what we want to see.
So since we have shown that the water is oscillating at half the frequency of the driver, we can assume it's a parametric oscillator. But how exactly does this stack up against the pendulum? Here I've divided pretty much the two phases of the oscillation of the water. We have the phase going up and the phase going down, both starting at the respective maxima and minima, and seeing the force of the driver, because right once it gets to the bottom, the driver starts forcing it back up, and right once it gets to the top, the driver starts forcing up again, and as it pushes through the equilibrium point, as we know. So obviously, to get from this one to this one, the driver drops and it water falls, and that's how that works. Now, as we saw with the pendulum, there was that extra force from the tension of the string adding to the velocity of the pendulum. But how does that work here? Well, we have gravity again, and gravity, assuming this is the center line in both of them. So these are the equilibrium. The top one's not particularly aligned, that's my bad. But gravity is going to pull the water above it in, and that's going to fill in the hole. So this water here and here is going to move in, and this water here is going to move out and flow out like that. And as you can see, it sort of flattens and goes there, flattens and goes there, respectively. Now, that's gravity. What the oscillator is doing when it's forcing it is also adding to the velocity in such the fact that as it increases here, it accelerates this bottom part up and this top part down towards equilibrium. So pretty much the more force it does, it adds more velocity to the water to spread as it goes. And then once it gets to equilibrium, the water doesn't just stop, the water keeps going in both the separate directions. So in this case, the water is going to go, and then it's going to go back up again, whereas this case it's going to go, and it's going to go up the sides. So that's how you get the translation into the next section of it. So as we see, the oscillator is adding more velocity to the water as it's pushing it towards equilibrium.
So we've shown that water can be modeled in a similar way to a parametric oscillator, such as a pendulum where the length is being modulated. So I guess I'll just leave you with these fun videos of different modes of the water at different frequencies for when it's oscillating. Thanks for watching.